Hi, welcome to the Bioinformatics Chat. My guest today is Guillaume Filion. Guillaume recently published a manuscript titled Analytic Combinatorics for Bioinformatics 1, Seeding Methods. And in this article, he applies analytic combinatorics, which we will talk in a minute what it is, and things called generating functions. So he applies that to the problem of finding the optimal seed length for read mapping. Guillaume, welcome to the podcast.
Hi, thank you very much for the opportunity, Roman. It's a pleasure to be here with you.
Yeah. So some people, even if they don't recognize you by your name, they will definitely recognize the title of your blog, which is The Grand Locus, in big red letters. I think I first came across it last year when I was searching for Burroughs-Wheeler index. And on the About page of your blog, you say that you're a scientist who loves biology and mathematics. So I'm curious to hear about your path as a scientist and how you came to be interested in both mathematics and biology.
Well, I guess that's a great question. I feel I'm representative of my generation in that sense because when I started my studies, it was in '98. Basically, bioinformatics did not really exist yet. Of course, there were a couple of people who were doing it before it actually existed, but everybody had the feeling in the community that it's going to be something big, but nobody really knows what it's going to be. And so there were a couple of programs, of teaching programs for PhD students, but also for earlier stages of education, like master's and bachelor degree, that were offering the possibility to go into the pre-bioinformatics. But I remind you that at that time, the genomes were not yet sequenced. We had only the genome of E. coli, of Drosophila, and that was it. And there was all this big fuss about the other genomes that were under construction, in a sense. And so there was all this excitement about the future of bioinformatics. Nobody really knew what it was, but they started to offer some trainings. And so this is how, let's say, I started a little bit in the field of bioinformatics from the beginning, basically ground up. I was in Lyon back then in France, and it was the second year they had opened this training program for bioinformatics. And so right from the beginning, I really thought this is the stuff I want to do. This is really what I'm really interested in, and what attracted me to it is, like I said, these promises of something really big happening thanks to the genomes that were sequenced and all these new technologies with the computers that were rapidly expanding. But also because I like the logics of it, really, as a biologist, which was my other part of the education. I really liked understanding how life works, but I always missed a little bit the formal logic of it. It's more like qualitative thinking, but not too much quantitative logic thinking. So I was really attracted to it. To this kind of mixing both from the beginning. And so the way it worked for me after that was that I did my studies until the PhD as a molecular biologist. So bioinformatics was just, let's say, 10-15% of my time, of my education, at least officially at the university. But on the evenings, I was doing the math because I was really interested in it. So since I'm 18 years old, I do about 1 hour of math every day to educate myself, let's say. And this is how I managed to keep a relatively okay level of math while still doing my career in biology. And so until PhD, my education is molecular biology experimentation, like the normal stuff with agarose gels, etc. And I liked it, but I was not super good at it. Still, I liked it. And after the end of my PhD, I decided, well, I really want a big change because I'm not really satisfied with the way things work in the experimental biology, because of the community, because of the science itself, because of the way things are done. And so I decided I want to do a big jump, and this is how I started to do pure bioinformatics from my postdoc. So I went to Amsterdam. And my supervisor of the time, Bas van Steensel, was nice enough to give me. He trusted me to do the jump. Basically, gave me 1 or 2 years to learn bioinformatics. No productivity was demanded at the time, so I had full license to learn as much as I wanted. And that has been really the key step has been at that point, because I switched completely to bioinformatics from a molecular biology background. And so we're talking of a year that was 2008. And I think, as I said in the beginning, this is quite representative of people of my age or my generation, that because there was not enough training in bioinformatics at the time, many people had to do it this way. Like you start with molecular biology and you spend 1 or 2 years of your life just to convert to something else. Nowadays, I don't think it works this way. But so that's how I became a bioinformatician, let's say. And then in 2012, when I started my own lab in Barcelona, I really had the vision that I want to continue to do both. I am myself not really good at the bench, but I really like it. I really like to think of experiments and to be able to do them in order to test our hypotheses, etc., in the lab. So I wanted to build a lab that was doing a bit of both, well, actually a lot of both. And this is how I started my blog. It was one idea to kind of collect a little bit of attention on the research we do, with a bit more emphasis on the bioinformatics side than on the biology, because on the experimental biology, because I've always found it really hard to attract good bioinformaticians. It's relatively easy to attract good experimenters, but it's really hard to attract good bioinformaticians, and that was the purpose in the beginning to kind of signal that we're doing this. And this is how I started to write about it a little bit on my blog. The post that you mentioned, for example, the Burroughs-Wheeler transform, is also kind of typical of what I like to write about, what I like to do on my blog. It's to edutainment in a sense, like to go really deep into the concept, into what happens, but also to kind of try and make it interesting a little bit and entertaining, I hope, for some people. And this is it. So still today, I'm doing my 1 hour of math every day to keep up with with the discipline of the math. And this is how this manuscript came out. Basically, it's in my free time, in my free hour of math every day. It's been incubating for quite some time.
I think it's very impressive that you were able to pick up the mathematics just by yourself, by doing, as you say, 1 hour a day. And it should be very encouraging to people who listen to this. I'm sure some of the listeners will find the subject a bit hard and maybe daunting.
Yeah, exactly. So yeah, it is difficult. Let's be honest. Math is hard. Logic is difficult, and all these things. They're very hard topics. What it takes is discipline, basically. With the years, I've realized that you don't really need to be super smart, but you need to have the discipline and to not give up. I think this is the most important message. You have to find the ways to continue making progress, no matter how much you fail, basically. But I'd say this is the same for the whole of research in general.
Yeah, absolutely. And your article specifically deals with the problem of read mapping. So where does that interest come from?
Yeah, it's also a very good question. Part of our research is, like most of what we do is experimental, but we very often have problems that deal with DNA sequencing. And so we needed to solve a couple of problems that were important for us for the technology that we developed in the lab. And the very first that we needed to tackle is some problem with sequence clustering. So when I started my lab, so we focused on that problem, and we gave an okay solution, at least something that works for us, and that started my interest in DNA alignment. I really thought it was easy when I started. I thought, well, BLAST is everything there is, and all the rest is really not interesting. But by looking into it, by seeing how subtle this can be, and how many different ways there are to solve that problem, I started to get a taste for it. So once we solved this problem of small sequence clustering, or at least gave a solution to it, then we were already contaminated in the lab by the big ideas of alignment, how we can do this better. And we don't really have an application in the lab, to be honest, for read alignment. But we always had a very strong interest in this to make these algorithms better. Just because we spend most of our computational resources aligning reads. I guess most of the planet does this at the moment. I'd be happy to have some statistics about it. But like Illumina represents most of the sequencing output, and I guess the next thing you do with your FASTQ files is to align them to some reference. And so we always felt like if we could bring even a small contribution to that, we can actually save a lot of computational time on the planet. So in the background of our minds, we're always thinking a little bit about this. And the only application we may have for it is for high-C. We do a lot of high-C, these techniques for a 3D structure of the genome. And we were always thinking maybe there's a way to make a tailored mapping algorithm for high-C, because there's a couple of constraints on the problems that you don't have in other cases. So we could use it for faster, better, or etc. And so we've been trying to make a mapper for high-C for a couple of years now, but it's because it's low priority, we're not making a lot of progress. We just think about it sometimes, and this is how these we came to brainstorm and bounce these ideas.
So let's introduce the problem that you're trying to solve. So what is seeding, and why do we need to optimize the seed length?
Yeah, again, another great question. So the problem of DNA alignment is a complicated problem. It's an n-square problem. Nobody has found a better solution to find the optimal alignment between two sequences that beats n-square complexity, where n is the length of the sequences. So when you have two short sequences, this is trivial. This goes really fast. But when one of these sequences is really long, let's say a genome, then already the n-square property makes it quite slow. And since the 80s, people have been thinking of how to beat that, how to go a little bit faster than this, especially when you have either two very large sequences or one very large sequence and a lot of small sequences to align to this, like in the case of the genome. And seeding methods, kind of rapidly the community settled around this heuristic. So it's a way to make the alignment much faster, but then there's a cost. If you use the standard dynamic programming methods, you're sure you're going to get the best alignment, that's for sure, but it's going to be slow. So now if you accept a certain risk of not getting the best alignment, it can be a small risk, let's say much less than 1%, for example, but you can gain an enormous amount of speed. And so this is the general concept and idea of developing heuristics. So it's inexact algorithms that are much faster, but they have a risk of not giving you the optimal solution. So seeding has been kind of the de facto consensus of what is the best way to speed up the alignment algorithms since the 80s. And the way it works is that instead of aligning the two sequences together, you're going to try and find short, perfect alignment, perfect match between the two sequences. So you chop the smaller sequence in small pieces, and you're going to try and find perfect matches of these small pieces with the genome, for example. And this, it goes much faster because in practice, it's much, much easier to find perfect matches than to find imperfect matches. So everything is based on that idea that finding perfect matches is faster than finding imperfect matches. So once you've chopped your small sequence into even smaller pieces, you look for perfect matches in the bigger sequence. And when you find a cluster of small matches, then you may think, okay, maybe my sequence will be perfectly nudged in this cluster. And you try the local alignment, you try the alignment method, which are slow, but only locally, not globally. So that's the whole principle. And today, as far as I know, all the short read mappers work with this method, because it would be way, way too slow to try and find for every read that you have sequenced to find the optimal, to be 100% that you have the optimal alignment with the genome. So all the algorithms that I'm aware of are using this method, this heuristic, and it's about 50% of the time. Let's say depends on the algorithm, of course. When we do rapid benchmarks with BWA, etc., and similar programs, it looks like the program spends about 50% of the time on the seeding part, and then another 50% of the time on the local alignment part.
And so you say, both in our email conversation and in your manuscript, that this problem of finding the optimal seed length, it was solved for BLAST, but not for read mapping. So what makes these two problems different?
Yeah, I was wondering as well, because it really looks like they're the same. The way BLAST works is that the protein is chopped into smaller pieces, and each piece is given a score, and this thing is aligned to the database of proteins of non-redundant proteins that is in the so the non-redundant sequences that are in the database. And I've been thinking for a long time exactly why the problems are not quite similar, not much less as what it looks. And right now, I can't really remember what's the fundamental reason why they're different. Maybe it's going to come back at some point. But let's say the fundamental difference why we can't just use BLAST to align short reads in the genome right now. I can't tell you.
Right. So my question is rather, why can't we use the same method, not necessarily use BLAST itself to align reads, but to use their method of finding the optimal seed length? Why can't that be applied to read mappers? Because you develop the mathematical theory where it's possible to give an approximate but asymptotically correct answer to the question of what's the probability to miss the correct site if we pick this particular seed length. And I think the BLAST authors solved this more or less computationally, right? Just by doing random simulations. Surely that's possible for read mapping as well, right?
Yeah, of course it is. Of course it is. The way BLAST solve it is actually not by doing random simulations. They worked out the math. It's very elegant. They used a theory that's based on the random walks, on the random walk theory, and this is how they can compute let's say not the optimal score, but they can compute the null distribution of the score if your two sequences are not related. So they have a distribution of what it should be, and if your score beats that, then you have a hit. Let's say at least you can associate a p-value or an expectation value based on the score that you observe compared to what you expect. And surprisingly, they did not really do this with simulations, but they did this mathematically by using random walks. This is actually the difference between FASTA and BLAST. FASTA was using simulations to get the score, and this is why it was so slow, because every time it was resampling the sequence and kind of querying it again in the database. But it was not working very, very fast. So BLAST solved that problem. You needed to query the sequence only once, and then you immediately had the score or the p-value for you hit. So it's almost the same problem with the read mapping, and the tiny differences are the following. The first is that when you do a read mapping, you're looking for a single place where it's going to go in the genome. What BLAST solves is to find local alignment. So it kind of chops the protein into small pieces like protein domains, and it tries to find if there is any homology with that particular piece of the protein. It's okay to chop the protein into smaller pieces, let's say 5 or 6, doesn't matter very much, because each part of the protein will have its own, let's say, its own hit. Okay, the fact that they're in the same protein doesn't really matter very much, because the protein is really chopped into smaller pieces. In the case of a read, you can't really do that. You're solving the global alignment problem. It's not completely true because the reads themselves can be chimeric, they can be split into smaller pieces. But from the computational point of view, the problem you're solving is not the local alignment problem, but more the global alignment problem as far as the read is concerned. The other thing is that in the case of BLAST, the null model is based on evolution. So they have computed the transition probabilities between the amino acids, assuming that proteins evolve with natural selection and all the process that we know. And so they have been able to compute the probability that an alanine goes to, an isoleucine or something like that with a certain amount of time or etc. So they have scores for this that took a long time to develop. And these are, let's say, they're kind of set in the BLAST algorithm. In the case of the short read alignment, The problem is that you don't know the errors that are made by the program. And so it means that you can't really set anything in stone for the problem that you have. But still, you could say, for example, that most of the reads are done with Illumina, and then we know that there's about 1 to 2% substitution rates with most of the Illumina sequencers. So it could have been possible to do something like that. But somehow, nobody has thought it was a good idea because the instruments keep changing. And so I think nobody's comfortable with putting this directly in stone directly in the software for mapping the reads. So I guess these are the two main differences between how BLAST works and how the short read alignments work. And you can't just use exactly the same concepts and plug them into the problem.
Yeah, got it. So I guess, the main difference is the difference between local alignment and global alignment, right? Because your second difference, sure, it's true, but if anything, it would make BLAST harder, like this problem for BLAST harder, because you have all these substitutions with different weights, whereas your error model, at least the model you describe in the manuscript, is, I think, relatively simple.
Oh, it's much more. Yeah, of course, it's much simpler than protein evolution.
And so the practical outcome of your work is that you come up with almost a formula, except it requires to solve a polynomial equation, but it's almost a formula to estimate the chance of missing a true read mapping, right, for a given seed length, for a given read length. And so how would the general population use your results? So I'm thinking you could create like a web page where someone could enter their parameters and get the distribution of seed length that they could use. Because if everyone who wants to take advantage of this has to figure out how to numerically solve this polynomial equation, it's I don't see getting much traction. So how do you plan to productionize this?
Yeah, so the main result, you described it very well. It's almost a formula, but not quite. You still have a mini problem to solve, and this is you got a polynomial equation, and you still need to solve it. The way the manuscript is written today, I guess, is completely useless for most people. Like it's quite interesting to see how things work, but practical applications, it would be way too much for them to implement the things that are in there. So that the point is, of course, to go beyond that. What you suggest is a good idea, to have a kind of a server that says, here, like you got this bit size, you've got that particular error rate, and you want this particular seed length, and here's your numbers. These are the probabilities that you'll miss the seed, that you won't have a seed that really matches to the proper location in the read. These are the probabilities that you'll make this type of error, etc. That could be one. Ideally, I'd like to make it a library, like written in a fast language, but that works for Python, C, or etc. So I'm working on it. I'd like to make a library so that you just call the functions, and then you get instantly the answers, so that you can actually copy paste the code in your favorite mapper, your favorite tool, so that you can estimate the parameters on the fly. I think that's really important. The way I see future progress in bioinformatics is, of course, by better algorithms, faster methods, better data structures, etc. But we need to make a lot of effort on the user interface. And one of the particular things that bugs me every time when I use so many pieces of software that are written by the community is the horrible high number of parameters. Like sometimes you have to tweak 20, 30, even more parameters to even get something sensible. So it's great because you got full flexibility, but sometimes you would like to have the auto-tune button. Like these are not super complicated problems. It's just that you need to have a human that checks, is this better, is this not better, etc. And this ends up taking hours and hours, easily hours of work in cases where you could just say, okay, please auto-tune the stuff, run the software and give me the optimum. Like I don't need to do it manually. And that would be the goal. The end goal would be to be able to have these numbers computed relatively fast with relatively few computational resources, so that the programs could call the functions and just make a couple of comparisons. Okay, if I use seeds of that length, then the program's going to take that much time to run, and will have that much probability of false positive, false negatives, etc. And then based on this, picking a decision. And so either auto-tuning, so that the user does not have to make these decisions for themselves, or giving the user a couple of options, saying, okay, here's your trade-off. If you want to run really fast, like it's going to be done in that much time, let's say an hour, but then 50% of your reads will not be right. And if you have the time, and this is really important for you to have high quality result, they will take, 3 days, and then you're going to have only 1% of the reads that will be misplaced. I think this kind of information is useful for the user, to really have something that makes sense for them, which are time, probabilities, etc. But if you tell them just the value of the parameters, like k equals 15 and m equals 19, that doesn't speak to anybody.
Yeah.
So that's the goal.
Cool. And I think I saw this idea in a remapping tool called QShow2.
Mm-hmm.
So they say exactly what you just said, that we want to auto-tune our seed length, but then they use an error model which is much simpler and is very crude compared to what you describe in your manuscript. So I think that they would totally benefit from a library like that if they could just plug it in their read mapping tool.
Yeah, and there are many ways to do it, of course. And you can actually get away with it by doing a little simulation. It works fine, probably. The read mapping are quite long when you think about it. You're up for a couple of hours of mapping most of the time. So you could just try different things on, 100,000 reads or a small number, a million, something like this. See what works best, and then when you found it, you map the rest of the file with the conditions that you found. Mm-hmm. So that nowadays we could do this. Of course, it's not really a big issue. It's just that we can do it a little bit better, a little bit faster with these methods. To be honest, let's say the true gain of the manuscript, I don't expect it to be really enormous, because all these things we can do in other ways. It's not like we have broken a technological lock or something like this. Like, we can already most of these things in other ways. It's just that this will be a little bit less wasteful if we use methods that are kind of pre-computed. And also is the real purpose of the manuscript is, of course, to show how analytic combinatorics works and how we can use it for bioinformatics for real world problems. So I hope that that this is not the last idea that people have on how to use analytic combinatorics.
Yeah, it's such a beautiful theory, and you do a very good job of introducing. So this is not like a typical academic paper that is very terse, and if you want to learn more, just go read a textbook. But you really put a lot of effort into explaining these concepts and giving a lot of examples, so people really can understand what's going on there. And I absolutely agree that this is probably the main benefit of your work, and I would encourage everyone to read it. And we'll get into some details a bit later. But speaking of practical considerations, so you rely on knowing the error distribution, the various parameters of like how errors can occur. And for substitution errors, I guess you could just look at the quality scores. But what about like insertion or deletion errors? How would you estimate those parameters in practice?
Yeah, I tend to not believe at all the quality scores. This is the first thing I remove from the FASTQ file. I'm not convinced at all by this thing. I always map FASTA files, to be honest. I never actually care about the quality scores. I had too many problems with it. So I think the only way to estimate the parameters of the errors, like how many insertions, how many deletions, how many substitutions, in what context, etc., is to align the reads. So you have to find some kind of very general parameters to map the first few reads. And when you've got a couple of alignment, then your numbers start to be accurate. You will see how often you get an insertion, how often you get a deletion, how many nucleotides are deleted every time you get a deletion, etc. So kind of the proof is in the pudding type of approach. You first try it, see what you get your numbers from what you've learned, and then you start all over again with these numbers.
Then you assume that there is the ground truth in the data, right? So you would set these parameters to the most lax values so that each read definitely maps somewhere, and then you just assume that that is where the read comes from, right?
Yeah, and then you make an error, of course, like because there's the reads that you haven't mapped. It may be because they've got too many mutations, too many errors. Sorry, and so of course you're going to underestimate the amount of errors when you do that. But at least they will give you the right ballpark. You know, if you know that you've taken a sequence from a particular genome, and that you really trust that you have only the 1 to 2% Illumina error rate, then that's good. You know what you expect. But most of the time, you have the reference genome, but the actual genome from which you take the sequence is one in the population. So you also have the SNPs, you also have other things.
Yeah.
So you've got all sorts of other errors that are coming from the experiment, from the way it was done, and from plenty of other things, from the mutation rate of the PCR and all these things. So your error rate of the instrument is not always the one that dominates. In practice, it does most of the time because it's much higher than the rest. But there are some problems in which you're not really able to know the error rate before you start. And so that's the way I see it, that you should just try at least get the numbers kind of right, plus or minus a couple of percent, and start from there. But of course, you can't estimate this super accurately. I'd say within the error rates, if they're accurate within 10% of the actual value, this is really quite impressive.
For read mapping, you don't really care about this split between genetic variation and instrument errors because they just are combined to produce your, for example, substitution rate. And for this problem, you don't care.
No, indeed. That's the point, that really an error is an error. Like a difference is a difference. It doesn't really matter where it comes from.
So your preprint, as I mentioned, it has this unusual form. It reads more like lecture notes than an academic paper. It's very detailed, very pedagogical. And I'm curious, what are your plans regarding this? Are you going to try and publish this as a paper, or what's the fate of this?
Well, I hope to be able to publish this in more useful papers. First, that they would be reviewed. Second, published in academic journals. I hope so. When I started to work on this, I realized I need to do it this way with a relatively big preprint. In the end, it's kind of 70 pages or so, with a lot of detail to explain the whole theory. And the reason I was thinking this is because pretty much nobody really knows what analytic combinatorics is in the bioinformatic community, and there's not really any obvious application for now. So I thought this thing for me belongs to the future. Right now, the audience for this type of work is relatively small, so I'm better off kind of trying to do as much theory as I can to explain it as clearly as I can right now, and put it on a preprint server so that it stays hopefully a couple of years until more people kind of know about these ideas, until it attracts a little bit more attention, and then they can go back to it and see that the concepts are clearly explained in almost a tutorial. I really wanted to write a tutorial about analytic combinatorics, so that they can refer to a central document that kind of explains to them how to get started with these ideas, etc. So it'd be ready there at the point when the community is big enough, the community of interest for this topic is big enough. So that was my plan. It was really to make it as didactic as possible on one hand, to explain the basic concepts as clearly as possible, but also to show a couple of advanced examples. So by the end of the manuscript, it becomes a little bit more difficult to understand because the examples are more and more involved. But it's also to show that there's no limit, basically. You can use these techniques for whatever you want. You can solve simple problems, but you can also attack really complicated problems if you want to spend the time and the resources on this. So the purpose of this document is just to be a reference, really a tutorial. I think that's the best way to describe it for people that will have an interest in bioinformatics, for understanding how analytic combinatorics works and what they can do with it. Examples, what they can do with it. What comes next? So first off, it says 1 applications to seeding, because there will be a 2, which will be for methods in multiple dimensions. So all the things I show in this preprint here are analytic combinatorics with a single variable, but you also have methods for multiple variable. So the second preprint will be about these methods and some applications to genome assembly and to clustering in 1D problems. Now, for the particular work that is in the manuscript, I would like to make maybe 2 articles with it. One that really explains the basic concepts. Let's say the main ones being, of course, the weighted generating function, but also the other ones that are a little bit more tailored to that particular problem of sequences and read mapping. And another one that would actually be useful with a real piece of software that computes the probabilities of different kinds of errors based on the type of error models that you have with the read. So telling you, with this error model, with such and such probabilities of insertion, deletions, substitutions, you will have so many % of the time a read that you can't map, and so many % of the time a read that maps at the wrong location.
Yeah. And regarding how you yourself came across analytic combinatorics, I know you have a very curious story about that. Do you want to tell it?
Yeah, sure. So it was 3 to 4 years ago at the beginning of Coursera. Back then, they were really trying to advertise this model of massive online education, open education. And so they were proposing a lot of courses, and everything was pretty much for free. You just had to click on the button, and the next thing you had the videos, and you can start learning. So I got very, very enthusiastic about these things when that started. Now it is a little bit less because it's more complicated. They have formalized it a little bit more. You need to pay, you need to follow track courses, etc. And it's a little bit more complicated. But back then there was the jungle. You could just download whatever you wanted, watch and learn. And I followed a couple of classes on things that are not really my expertise. And this was one of them. This was a course by Robert Sedgwick. It's 2 courses actually that he put on Coursera, and it took me quite some time to follow it and to understand it. What I really liked about it is that I felt at the end of the course that I hadn't taken everything out of it. Most of the time when I took a class on Coursera, after the final watching the last video, I really had the impression that's okay. Now I understand how these things work, and I got a good overview of the field of whatever they wanted to present, and I mastered this good enough. But in the case of that particular course, it was pretty obvious that I really hadn't gotten the essence of it yet. That I felt I need to spend more hours on this to understand what we can do with it, because I feel this is very interesting, but I'm not able to really use it for anything practical. So I bought the books that are associated with the Coursera class, and I started to read them. And I was pretty sure that I would be done reading the book in about 1 or 2 months. But so it's been 1 year and a half now, and I'm only halfway through the first book out of 2, about halfway, because it's so dense. It's really so dense and so full of let's say mathematical wisdom. I'm not sure that will speak to many people, but that's really the way I felt it. That every exercise, every word is really, really dense. These 2 authors, so it's Robert Sedgwick and Philippe Flageolet. They really managed to make something that is really dense and that is worth spending the hours thinking about. And so it's in the middle of this. Let's say halfway through the first book, that the ideas finally started to combine for me, and to say, okay, now I understand this well enough so that I can start to think of real applications for what we do in bioinformatics.
I think by now we piqued our listeners' interest in analytic combinatorics. So let's dive a bit into it and maybe explain a couple of concepts to give a feel for it. So one of the central objects in analytic combinatorics is a generating function. Can you explain roughly what that is?
Yeah, this one is complicated. This one is complicated. Well, everything is complicated, of course, because now we're just talking. And it's very difficult. Most people find it quite hard to explain, even when they have a whiteboard and they've got a PowerPoint or something like this. So just by talking is going to be a little bit difficult, but we'll try. The way I do this when I have to explain this in a seminar or something like this is as to really roll back to what is science, even what is thinking in reality. How does science work?
Oh, wow.
And science would never really solve problems. We don't really solve problems. What we do is we translate problems in a world in which we can solve them. We solve them in this world, and then we translate them back in the real world. So pretty much everything works like that, even experimental biology. So you want to solve the problem of a particular sickness, but you don't start like that, not at all. The first thing you do is you make a model for it. You choose a model organism, and you make sure that you can represent some of the features of the real sickness in your model organism, and you study it there. You don't really study it on the patient because it's much more efficient. And in your kind of transformed problem, which is like your silly mouse with its silly problem that's not really a patient, then you find the solution in that context. And once you found the solution in this context, you translate it back to patients because it's much more efficient to work this way. And we don't really know how to solve direct problems. We always translate them into a framework where we know we can find the solution. We find the solution in this framework, and then we translate back. So that's one example with model organisms in biology, but math works this way. The Fourier transform, this is exactly what it is. You got a problem that's really complicated in one space. You do the Fourier transform, and then suddenly everything becomes super easy. You can do whatever you want, transformations on this problem, and it becomes relatively simple to solve it in a different space. Once you have the solution in that different space, you translate it back into the initial problem that you had. Or, the eigenvalue decomposition is, again, one other problem of this. You just find a space in which your matrix has a simple representation. Everything becomes easy. You can solve the problems easier, and then you translate it back to the initial problem. So as far as I know, everybody does this all the time. That's the way we solve problems. We never solve them directly. We always find a model, a representation for the problem, and a space where the solution will be easy. So that's exactly the concept of generating functions, or weighted generating functions in the document that I wrote. You have a combinatorial problem, and these problems, you can try and attack them directly, but most likely it's going to be difficult, cumbersome. You're going to fail because you're going to have long equations, and things are going to be just complicated, basically. So you transform the problem into a space where everything will become easy. And this is exactly what the generating function does. So that's the why of the generating function. It doesn't tell you what it is, but at least it tells you why we do it. Now, what is it? It's just a way to count things. Okay, so we count 1, 2, 3. So we use numbers to count things, but there are other ways to count. And in particular, when you want to count infinite sequences, let's say the sequence that would be 1, 2, 4, 8, 16, etc., the powers of 2, you have different ways of writing it. And the one way would be to write all the numbers. Of course, you can, because there's an infinite amount of them. Another way would be to use a function representation of these numbers. And you would say this is, for example, 1 times x plus 2 times x squared plus 4 times x to the power 3 plus 8 times x to the power 4, etc. So you just use a Taylor representation in which you've got a variable. In the case that I just said, it's the variable x, and the coefficients of this Taylor representation is the initial series of numbers that you were interested in. And that really is what a generating function is. It's just a way to associate a series of numbers, 1, 2, 4, 8, etc., to a function thanks to the Taylor series representation. And the point is that you've got exactly the same information in the original sequence of numbers as you have in the function, because there's a one-to-one correspondence between the two. So it's exactly the same amount of information, but one of them is really, really big. You can't even write them all. The other one is really compact because you can write a function for this.
Yeah, but this is just part of the story, because it's good that they are in one-to-one correspondence, but then the question is like, why do you have to consider a function versus just a sequence? Why do you have to multiply these numbers by powers of x and then add them up right? And I think the answer is that it just happens so that mathematical operations on these functions like addition and multiplication translate to very useful operations on these numbers and these sequences.
Exactly. That's the whole point of the idea, is that when you do this transformation to say I start from a sequence of numbers on which I could not do many operations, not many combinations, etc. If I turn it into that particular function, then I made myself a really nice gift, because with these functions, I'm able to make operations that will correspond to relatively complex things in terms of sequences of numbers, but relatively simple operations when they're considered as functions. So, for example, when you want to take two objects and you want to concatenate them, then that corresponds to taking the generating function of the first object and multiplying it by the generating function of the second object. So this is really analogous to, for those who know of the Fourier transform, that the multiplication in the Fourier space corresponds to the convolution in the sequence space. And convolution is a pretty complicated operation to perform, but multiplication is a relatively simple operation to perform. And so it's the same idea that once you've transformed your sequences to functions, then by just doing multiplications, additions mostly, and divisions, you will be able to perform relatively complicated combinations of operations on your initial sequences.
Yeah, and in fact, the product of generating functions also gives you a convolution of the sequences. So I actually haven't thought about it this way before, but this analogy is really interesting because it goes deeper, and I wonder whether there are some deep mathematical connection. But you're right, both Fourier transform and generating functions give you convolutions.
Yeah, absolutely. So the multiplication of two generating functions is a convolution.
Right, and I'm sure. So there is a presentation of discrete Fourier transform in terms of polynomials and multiplication of polynomials. I think there is an excellent lecture by Dan Gusfield. I don't know if you saw that.
Nope.
Where he motivates and basically derives the discrete Fourier transform through polynomials and their roots and their coefficients.
Yeah, absolutely. You can do it this way, indeed, and then you can replace the free variable by the nth root of one. I'm not sure how it's called exactly. So like the complex number that raised to the power n is equal to 1, and you just replace the free variable with this, and you get the Fourier transform. So there is definitely a very strong relation between the two, but let's say the strongest relation is really philosophically. They want to do the same thing, and they use the same methodology to do it.
Mm-hmm. Yeah, and another useful way I found to think about this is that the generating function generalizes the notion of probability, because if you have two events which are independent and have certain probabilities, then the combination of events has the probability of the product of probabilities. But then when you assign sizes to these events, right, then a generating function allows you to keep track of probability for every size. But then you also multiply generating functions, but now it gives you probability for each size, and the size is always a combination. So if you have a combination of two events, then the size of this combination is the sum of the sizes. And so this is where the convolution arises, because if you want to get total size of 5, you can do this either by picking event of size 0 from the first set and size 5 from the second set, or 1 and 4, or 2 and 3. And so you have to consider all these combinations and multiply their probabilities and add them up. So in this way, a generating function is a probability that also keeps track of the size of the object.
Yeah, I didn't think about it this way, but this is right. That you could say it's a generalization. Let's say it's a little bit more of an extension of probabilities, because you don't just keep track of the probabilities of the events, but also you associate to them a variable, which is the size, for example, or some feature. You can add more. So of course the size in the manuscript that I wrote is the essential one, but you can even do this with more than just one variable. This is also something that I wanted to touch upon in the very last section of the manuscript to show that you can also associate these probabilities with not just the size, but other events. Let's say the total number of errors in the read or something like this. So it's indeed a very good way to think about it. It's kind of probabilities with labels in a sense.
Yeah, and another application, I don't know if you thought about it. You have this example in your tutorial where you consider two objects, one with probability P and the other is with probability Q. And so the combination, you get this expression P squared plus 2PQ plus Q squared. And that, of course, reminds us of the Hardy-Weinberg equation.
Mm-hmm.
And so I thought that this is a very, well, not exactly this, but if you add a second variable, this becomes a good way to derive and formulate the Hardy-Weinberg equation, because I often see, for example, when biologists who are not also mathematics enthusiasts like you, when they write down the Hardy-Weinberg equation, they often write it down as P squared plus 2PQ plus Q squared equals 1. And that, of course, is not the Hardy-Weinberg law. It's just a simple algebraic identity, but that doesn't tell you that P squared is the frequency of this homozygous, combination. So in order to express this formally, you just add two variables, and now you can separate this P squared and 2PQ. So it's not just a sum of numbers, but it's a formal combination. So you get P squared capital A squared, right, plus 2PQ capital A small a plus Q squared small a squared.
Yeah, it's a very good idea. I don't really think we can explain Hardy-Weinberg thanks to analytic combinatorics, but probably we can explain analytic combinatorics with Hardy-Weinberg, because most biologists at least are comfortable with this concept. It's exactly the same indeed. Like the size now is the number of alleles of capital A or small a. So you either have 0, 1, or 2. And this is exactly the point indeed.
Yeah, and then maybe you could derive something more complicated than Hardy-Weinberg. I honestly don't know, but could be.
Yeah, of course. I haven't thought about this too much, to be honest. Everything that has some level of formal thinking can potentially benefit from analytic combinatorics. And I'm myself not. I don't know enough about population genetics. I love it, but I don't know enough about it. And maybe there are some problems that we could solve with it, or some evolutionary model, etc. One thing is that in the manuscript that I just published on bioRxiv, it's only about sequences, because I'm concerned with the DNA sequences. But analytic combinatorics has a huge area with trees. Actually, most of the time, they start by explaining how trees work and how you can use analytic combinatorics to very, very efficiently solve problems with trees. And it's quite interesting because it's based on recursions, and I guess this is why the teachers prefer to start with trees, because it immediately shows the benefit. The problems are really, really hard to solve without analytic combinatorics. But as soon as you use some kind of recursion thinking, and you can write the generating function of the trees, everything becomes really easy.
Yeah, and let's touch on the second important concept from your tutorial, which is the transfer graph. So do you want to try to explain what transfer graph is and why we need it?
Yeah, so the concept of a transfer graph, it's kind of new. So this is the one that I didn't see anywhere before. So it may actually be a novel concept. Of course, it's very, very difficult to have new ideas. I'm pretty sure that something equivalent has been written somewhere else. And it's based on a concept of a transfer matrix. But when I was writing the manuscript, I realized it's pretty difficult to explain how transfer matrices work, because they're quite formal, and for the audience that really wants to have concrete explanations, it's not working very well. So I immediately decided to represent them in a formal way by doing a transfer graph. And the idea of a transfer graph is really to represent sequences. So you can imagine that you're playing Lego or something like this, and you have some very simple Lego with only two ends, a beginning and an end. You cannot combine them in more ways, but you got different colors. You got 2, 3, 4 colors. and you would like to describe to a friend of yours some sort of sequences of Lego that you can build. And you would say, for example, I want you to build all the sequences such that you never put a blue block after a green block. You can do anything you want, but you can never put a blue block after a green block. So how would you write this? So you'd actually send to your friend a graph with all the colors of block that are possible, and you would put an arrow every time a block can follow another. So the yellow block would have an arrow to the blue block, because you can put a blue block after a yellow block. So you put all the arrows from which you can do combinations of the blocks that can follow each other, but you would not put an arrow between the blue block and the green block, because this is not allowed. And so how your friend would then create these sequences is by just following the arrows on the graph. Okay, so you just start from the beginning and you just keep following the arrows. And for any particular path that you've gone through this graph, you have constructed one particular sequence of Lego blocks, which never violates the constraint that there should not be a blue block after a green block.
Yeah, so that's basically a finite automaton.
Yeah. That's I think it's more of a augmented finite automaton, because the edges can be quite complex. The one that I just described is a finite automaton, exactly. In the case of a transfer graph, the edges can be complicated objects, complex objects, because the edges are weighted generating functions. And this can already be much more than a simple object. They can be a tree, they can be a sequence of trees, they can be cycles of sequences of trees or something like this. So you have a little bit more flexibility in the letters, right? So it's a way to maybe extend this a little bit beyond just the finite alphabet, because now you can start to put relatively complex objects after each other. But it's exactly the concept of a finite automaton.
Yeah, and I also think that this analogy between generating functions and probabilities works very well here, because if you replace in your transfer graph and transfer matrix generating functions with just simple probabilities, you get Markov chains and the transition matrices for Markov chains, and they're of course very familiar and especially even applied to DNA sequences, right? People use
exactly
Markov models, hidden Markov models all the time. So this is just Markov chains, but where you generalize the probability to this generating function that also keeps track of the size.
Yeah, exactly. That's exactly the idea. So one path through a transfer graph would correspond to one particular chain in a Markov chain model. But now you have extended a little bit the constraint of having only probabilities for the jumps with having complex objects, which themselves have complex probabilities.
Yeah.
And the advantage is that it doesn't feel so complicated. Like the whole point of this in reality is not really to solve problems that we could not solve. I think most of the things that I touch upon in the manuscript, we had ways to solve them, like one way or another, even by throwing just computational, like very big computers at it. It's pretty obvious that we could have done this. But it's a little bit the opposite of machine learning. Okay, in machine learning, like you can solve the problems, but you don't understand how that works. With these approaches, you really understand what you're doing. Of course, there's a bit of a black box somewhere in how the mathematics work, but the point is that you can put intuition to kind of, raise the level of intuition of what you can do, what you cannot do with your problems. That's the whole point. So these transfer graphs in reality are fairly simple. We can even represent them on a piece of paper most of the time, and yet they represent fairly advanced, fairly complex objects.
And when applied to the problem of seeding, so you gave this example with like a green block and a blue block, and I guess that translates to a error-free region, right? So the correct region of the read, and they must alternate with errors and error regions. So just to give our listeners an idea where these graphs arise in seeding problems and how they apply.
Yeah, exactly. That's the point. You could say you're building sequences of Lego blocks with only two colors. The red one would be the ones that have an error, and the white one are the ones that don't have an error. So you could say if you want to have a seed that's going to work for your read, you need to have at least, let's say, 20 nucleotides without error to be able to map them uniquely. Remember that the seeds are based on exact matching most of the time. So you need to have no error with at least 20 nucleotides in a row. So in that case, you're describing a graph in which you must put at least 20 white blocks in a row so that you have a seed. Or you can do the reverse. That's what I do in the document. I'm describing the reads that don't have a seed, which means you're never allowed to put more than 19 white blocks in a row. Every time you put 19, you have to put a red block after that, so that there is nowhere in the read, nowhere in the sequence, 20 blocks without an error, or 20 white blocks in the case of the formal thinking. So you just describe a graph in which it's impossible, by just going randomly at whatever you want, all the paths, you can never have more than 19 white blocks in a row.
And this is, of course, possible exactly because the generating function tracks the size of the object. So it's not just you have alternating green blocks and blue blocks, but you can say exactly that these green blocks are up to a certain size.
Right. That's exactly the point. That as we mentioned before, it's because you keep track of the size of the objects that makes it possible. Otherwise, it becomes quite complicated.
Yeah. And so just translating a problem into generating functions gives you a nice language to talk about it, but that doesn't immediately lead to a solution. But then there is this beautiful result, how you can actually extract a numeric estimate, because the quantities of interest in generating functions usually correspond to the coefficient in a certain series, right, around a certain power of the variable. So like ak times z to the power of k. And so you're interested in a specific z to the power of k, and you want to find the coefficient in front of that power. And by itself, if you try to compute that directly, you would perform the same computations that you would perform even if you didn't know about generating functions and would just work with the sequences. So usually that's not much benefit, right? But then you apply this result, I guess, from complex analysis to get the estimate. So can you describe that a little bit?
Yeah, of course. It's let's say it's really the core of analytic combinatorics. So far, we've described what is called the symbolic method, and you said it very nicely. It's a language. So now part of the theory is just to give you a language that tells you how you can combine things together, and there are tools just for doing this. And transfer matrices or transfer graphs is a tool for just doing that. It tells you how to build a map or a plan of a construction plan for your particular objects. Like we've said, a block of a certain color could not follow a block of another color, etc. So this is part of the symbolic method, and all it does is that it allows you to translate what you want to do with the real objects on what you have to do with their generating functions. But at the end, all you get is a generating function. You don't have the solution of your problem. You just have a generating function. But all these operations are made with one rule in mind, and you also said it very nicely, is that if you consider the function as a Taylor series, the solution of your problem is always the coefficients of that Taylor series. Right? So like this is really how these operations work. And once you've got your final generating function, you know one thing is that your solution is encapsulated in the coefficients of the Taylor series, and the problem becomes, how do I recover the coefficient of this Taylor series? And surprisingly, it's an idea that came around only in 1990 by Philippe Flageolet and Odlyzko. And of course, the idea was in the year before. But it seems that it really doesn't appear very much before this. And the idea is to use complex calculus. So you have your function, and in order to extract the coefficient of the Taylor series, you can use a whole lot of theorems that are out there, and they're fairly complicated. Most of the time, you'd have to derive the function. Let's say if you want the 30th term, you would have to derive the function 30 times, and that's really quite complicated. So that's not very interesting. So it seems a little bit that your coefficients are trapped in there. You can't really extract them easily. And so what Flageolet and Odlyzko realized is, if you're okay to have a very, very good approximation, so you don't want to have the exact solution, but you want to have an excellent approximation, then you can do this really simply. And so what do we mean by relatively good, like really good approximation, is that if you want the coefficient, let's say 30 or 50 or 100, they will become increasingly accurate. 30 will be already very good, but 50 will be exponentially better, and 100 will be exponentially more accurate than the previous two. And the way it works, the way Flageolet mostly realized this, is by looking at your function, not as a real function, but as a complex function. And you just have to find the singularities of the function. So that's the point where it's not defined, because the denominator is 0. You just look at the singularities, and once you've got the singularities, you have it. You pretty much have it. Then, with just the knowledge of the singularity of the function, you can describe extremely accurate approximation of the numbers you're looking for. It's fairly difficult to explain by just talking, etc. But the math is really not that complicated. For the simple case, I think everybody with 2 or 3 years of basic math can understand it fairly simply. The theorem is much, much more general than the one I gave in the manuscript. This is just a small version, which is completely sufficient for everything I do in the manuscript. But the theorem is much more general, and this is where the difficulty was. It was to realize how general this result is, that it doesn't even need to be on the relatively simple cases that I gave in the manuscript, that it works pretty much all the time, this method.
Yeah. So I hope by now we gave the listeners enough motivation and background to go and read your excellent tutorial. Before I let you go, you mentioned in our email conversation that you found a bug where the random generator was not random enough. So I'm very curious what that was and how you tracked it down.
Yeah, so for me, this work has been really pleasant. It's also been an eye-opener of what it means to be quantitative. Like I said, I'm a molecular biologist by training, and most of the science I do is qualitative. And qualitative science is really great because it's yes or no, and you don't really have much doubt about it. But I never really had a quantitative thinking. And for the first time with this work, I realized what it means to be quantitative with 4, 5, 6 digits precision or something like this. I realized how much information you have and how much you can tell about your problem and how much you're in control or how much you're not in control. And what's really nice about the methods of analytic combinatorics, the one that I'm showing in the manuscript, is that you have the degree of precision that you want. It's really up to you. I just described now the method of Flageolet and Altschul, which is to approximate the coefficients, but you also have the exact solution if you want to. That's the other benefit. It's a bit more work. You need to compute all the singularities, not just one. And in that case, you get the exact number. And the only thing that limits your precision in that case is the machine precision of your computer, which is, let's say, of the order of 10 to the minus 16 or something like that. So as long as you don't measure numbers that are smaller than 10 to the minus 16, then you're fine. You've got the pretty much exact solution of your problem. So when I was doing this work, I was also checking that I was not completely far off by doing simulations. And I could realize that there was this one problem where the result of the analytic combinatorics and the result of the simulations were off by 10 to the minus 3, something like this. Like there was an error on the third or maybe fourth digit. But I knew, the theory told me, this should be much smaller than this. It really cannot be that big. It has to be much smaller than this because I was using the complete solution of the analytic combinatorics. And so I, of course, thought that I did the math wrong, but in the end, by eliminating all the possibilities, it turned out that I was just using the random generator that comes with C. Like there is these the standard ones that are in the standard libraries, and these ones, I learned this afterwards, asking my colleagues. It's fairly known that they have a periodicity of 10 to the 8 or 10 to the 9, something like this. And because I was doing 10 to the 9 simulations to really get as much precision as I could, then I was just looping through the whole random generator, and I was not really getting any precision, quite the reverse. So it turned out that on this particular case, the math was correct, and I was able to detect the fact that the random generator was looping after 10 to the 8 iterations, something like this. And the solution just consisted in using the state-of-the-art random generators, which are machine twister, rather than the ones that come with C, and that solved it completely.
Very cool. So before we finish, anything else you'd like to talk about?
I think we covered most of the ground, really. As I said, I see this work really as a tutorial, and the most interesting part is definitely the first, for the people who want to get acquainted a little bit with what analytic combinatorics is, what you can do with it, what the central concepts are. And the second part is more to see what it can do, how far it can go. And I'm pretty sure it's just the beginning, that there will be people smarter than me that will find ways to use it for much more advanced problems and things that I hope we really cannot do any other way. Everything that I'm showing here is we could do it another way, but I really hope that at some point people will be able to push the boundaries of what we can do now with bioinformatics thanks to these tools.
Awesome. Well, Guillaume, I'm looking forward to your second work, and thank you so much for talking to me today.
Thanks so much. It was a pleasure.